Hello, my name is Shin. I'm a first-year master's degree student in Ocean Systems Engineering from Sejong University. I'm going to present a study on feature extraction suitable for the active sonar target classification today. This is the table of contents, 6 chapters from the background to the future plan. In this chapter, I'm going to explain the background of my study. For the active sonar data are very limited and insufficient in our field. Therefore, to overcome this problem, various feature extraction methods has been researched. As can be seen in the figure extraction method can give a variety of input signal into deep learning. From this study, I want to find out which feature domain is most appropriate feature for the active sonar target classification and suggest proper prior of feature domain. In this chapter, I'm going to explain the feature extraction method that I used. These are feature extraction methods that I used. From 1 to 3 are one-dimensional and 4 to 6 are two-dimensional. Timber-based feature is based on human auditory system. The reason why I choose this method is, from the paper survey I counted the number of data used in our field, and these are the most frequently used ones. The timber-based feature is unique feature extraction method that is used for the musical instruments, and also the Defense Research and Development of Canada investigated as well. From 3 feature distribution analysis by visualization, I'll focus on the uniform manifold approximation and projection. These are one-dimensional feature extraction methods, which are Mach frequency substrate coefficients, MFCC, gamma tone frequency substrate coefficients, GFCC, and substrat. MFCC based on specific human auditory system using MEL filter bank. GFCC have an improved filter bank from MFCC. Substrat is same as other substrate coefficients but without any filter bank. The follow flow charts represent how we extracted from the signal. And the figure represents MEL filter bank and gamma tone filter bank. As we can see, they are designed for the human auditory system, which has narrow bandwidth in lower frequency and otherwise. Now, these are two-dimensional feature extraction methods. Firstly, short-time Fourier transform. Short-time Fourier transform is the frequency analysis for the short interval of the signal. Secondly, wavelet packet decomposition. WPD is the decomposition of the wavelet basis function of the signal. Similarly, there is a discrete wavelet transform, but WPD goes through more filtering than DWT. And constant Q transform. Constant Q transform is the one-off spectrum analysis method, and this is how we can calculate constant Q. Same as other human auditory system-based features, this also has narrow bandwidth in lower frequency. Lastly, timber-based feature. I obtained one timber-based feature from 68 various audio descriptors as can be seen in the figure. These representations are based on human auditory system as well. And the descriptor is feature vector of each representation. To explain simple descriptor, spectral centroid is calculated as the center mass of the spectrum. Spectral spread is calculated as average deviation around the centroid. Also, spectral kurtosis is calculated as statistical measure of the transients, and also its location in frequency domain. I used 3 feature distribution analysis method by visualization. Principal component analysis. PCA is linear dimension reduction. And TSNE. TSNE uses T-distribution and nonlinear dimension reduction. And most importantly, uniform manifold approximation and projection. UMAP is the most recent and reliable analysis method between them. It uses a uniform distribution unlike others. Also, it uses manifold learning and topological data analysis. The following figure is visualized MNIST data set using UMAP. We can see the separation ability of UMAP here. In this chapter, I'm going to explain the data. The data is active sonar underwater data. I used around 300 target sample and 1000 non-target sample. The figure represents LFM signal of target and non-target signal. Non-target signal consists of clutter and noise. I framed each sample with 20 milliseconds with 50% overlapping with each other. From the following results, red dots represent the target and blue dots represent non-target. In this chapter, I show the result from feature visualization using active sonar data with feature distribution analysis. Firstly, it's visualized feature domain using principal component analysis (PCA). As I explained, red dot means target and blue dot are non-target, and the red empty circle represents the target crowd. As can be seen in the figure, their distribution seems similar to each other. Not one separates perfectly. Secondly, the plot represents feature visualized with t-SNE. I can see the difference with PCA on separation. If you may see the target crowd, timber-based feature separates target and non-target. Lastly, the features are visualized with UMAP. Our prior method of feature distribution analysis by visualization. If you may see the target crowd, the target and non-target of timber-based feature are separated perfectly. We can tell it is more reliable feature distribution can be observed than the PCA and t-SNE. To compare each feature domain numerically, I calculated the circle containing 90% of each target and non-target data points, red and blue empty circles. Euclidean distance of each center point is calculated to obtain overlapping area of two circles. The left figure represents the timber-based feature, and the right figure represents MFCC, both using UMAP. And the best and worst overlapping percentage. This is very rough approach though. Therefore, a more sophisticated approach will be adopted in the future. Now I will discuss the conclusion and the future plan. From the feature distribution analysis and its numerical results, the timber-based feature has the best separation ability with no overlapping area at all. However, each feature domain has different results to each other, so we can conclude which feature domain should get a prior for the active sonar target classification for the next step. For the next step and future plan, the more sophisticated way to compare feature domains using feature distribution analysis will be performed. Also, an accurate comparison of the performance of each feature domain will be required and performed using deep learning. This will suggest maybe the same prior or different prior feature domain we should go for. Furthermore, active sonar target classification combining feature domain, active learning, and deep learning is in our interest to obtain more automated and the better target classification. Thank you so much, and thank you for listening, and thank you for your time.